All right, so let me share my screen. And the screen is shared. That's good. Okay, how's everybody? Hope you guys have had a good weekend. Right. So let's start with a new topic, kinetics of particles. Still we are in this module 1, which is particles, but we are moving to kinetics. So far we study the motion, like acceleration, velocity, and position, without talking about forces. In this topic, we will talk about, or we study forces that acting on particles. And this topic, I'm sure, is not new, and the concepts are all, it's not new for you. It's going to be, again, a review, but with another fresh look at this concept. So making sure that you are ready. So when we move to rigid bodies, we are going to apply all these concepts again for rigid bodies, but in a different way, basically. All right, so when we talk about basically forces acting on the particles, and we want to find the reactions and so on, there are 3 ways that we can study this topic. One is the famous Newton's second law, which I'm sure everybody knows. And the second one, again, is work and energy. You've seen it in physics. Basically, what we said, work is equal to energy if there is no waste, basically, right? The change in energy, to be exact, which we call it conservation of energy or work and energy. And then impulse and momentum, the same again concept. If you apply a load with a certain time to an object, you create an impulse. This impulse move the subject, give this object a speed, which, because of its mass and this speed, we call it momentum. And these two has to be basically equal, which we call it conservation of impulse and momentum. Let's formulate this and see how we can use it to solve problems. So the first one, Newton's second law, is the famous formula of F is equal to ma. And I'm sure I need to explain it further. Forces is equal to mass multiplied by acceleration. Where the work and energy comes from, basically from the same formula. If I write this formula, let's say, you guys recall from our previous lecture, that we had a formula like this. V dV is equal to A dx. Do you remember that? We said velocity multiplied by derivation of velocity is equal to acceleration multiplied by dx. And we said this is a useful formula when we don't care about time. We want to find the relation between velocity, acceleration, and position. So from this formula, if let's call this one 1 and this one 2. So from formula 2, if I find A, basically A is equal to V dV divided by dx. And if I substitute this one in formula 1, so combination of formula 1 and 2, what do we get? So F will be equal to M and V dV divided by dx. So let's simplify it a little bit further. What do we get? F multiplied by dx is equal to mv dv. All right? This all multiply together. So this is basically a relation for a very short time or very short displacement, dx. But if I integral the whole things, what do I get? So what is f multiplied by dx? When I multiply f by displacement, what do I get? I'm sure you know what it is. Force multiplied by position. Any idea what it is?
Work.
Work, exactly. Thank Vasef. So as Vasef mentioned, we all know this is work, right? What about this side? So this side, if I simplify the integral, I can write m is a constant, right? And then integral of v dv is more like integral of x dx, right? So it's going to be half of m, let's call it from a speed v0 to v1, half of v1 squared minus half of m v0 squared. And you guys all know what this one is, right? This is energy. Which is basically kinetic energy, right? So as you can see, we started with the same formula, F equal to ma, and we saw that work is equal to energy. So what I'm trying to say, the second formula, work and energy, is basically the same concept as the first one. Newton's law is nothing new. And we can generalize it and say, if we generalize it, then what we will get is work is equal to change in energy. If there is no work, then change in energy is zero, and this is what we call it conservation of energy, right? So this is basically the same, the second method, work and energy, which we are going to use. What about the third one, impulse and momentum? Let's see if we can build up this concept from formula number one. So remember, when we talk about impulse, again, if you forget from physics, is we need to talk about time. How long basically we applying the load to an object. So let's say if I have an object, whatever object it is, let's say a particle, and let's say I'm applying a load F, and this load, I am applying this load for duration of, let's say, T. I'm going to write it here. We apply this load for T seconds. So what do we get? There is a new concept which we call it impulse, which its definition is force multiplied by time. So impulse, so if somebody is asking you, is force multiplied by time. If you apply the force for 10 seconds, you get an impulse. And let's see how we can use the same formula, formula one. So again, recall from previous topic that we define A, basically acceleration, as dv divided by dt, right? This is something that we know. Let's call this one formula 3. All right. So now let's substitute this A in formula 1. So from formula 1 and formula 3, what do I get? F equal to m dv divided by dt. And let's simplify it one more step. We get f multiplied by dt equal m dv. So what do we have on the left? Force multiplied by time. So recall again from formula 2, force multiplied by dx, we call it work. Force multiplied by time, we call it impulse. Right? Let's see what the other side looks like. Again, always we do integral. We are interested in basically a certain amount of time, not just a dt. dt is a tiny, small amount of time, just for developing our formula. In this course, we never use integral, basically. We just introduce them so you know where the formula comes from. So let me simplify this side. What do I get? Again, from a speed v0, I go to a speed v1. If I integral, m is constant, I get mv1 minus mv0. All right. And if you forget, again from physics, m multiplied by v is something that we call it momentum. Right? So energy was half of mv squared, but momentum is just mass multiplied by velocity. The bigger the mass, the bigger the momentum. The bigger the velocity, the larger the momentum, right? So this is momentum, this is momentum. So then what I can write is basically impulse is equal to change in momentum. And this is our basically third concept. So let's take a look at this page and see what we got. So we got the Newton's law, F is equal ma, right? And nice and clean and invented 200 years ago. Or no, not 200 years ago. Yeah, about. You can check history. And then somebody, he just replaced A by this formula from 2, V dV divided by dx, and proved that work is equal to change in energy. And then somebody else also used this formula, just replace A with the formula number 3, dV over dt. And he proved impulse is equal to the change in momentum, right? So you should have basically a good grasp of this concept. You are familiar with force. Force is a vector, right? You apply a force into an object based on its mass. Based on its mass, it's get an acceleration, okay? You apply a force to an object for a certain basically duration of time. It creates an impulse, all right? Like this one that I showed here. F, you apply F for a certain time, T. So it creates an impulse. This impulse is F multiplied by T, and it's equal to the change in momentum. You apply a load and move the object to a certain distance. So you have done some work, F multiplied by displacement, formula like number, let's say F multiplied by dx. And what you're creating is change in energy, like kinetic energy in this case, and we have the conservation of energy. Work is equal to change in energy. So you see, they are all connected. It's just different view that we have to all of these. You can solve the problem using momentum and impulse, or if you don't have any information about time, then why not using this relation work is equal to change in energy. If you don't care about the amount of work and you can just use the original formula, F equal to ma, that's the best. You just use the original formula number 1 without caring about the rest. because as you can see, method number 2 and 3, they are originated from the first one. Okay? Any question, guys, so far? I'm going to also check chat to make sure. So, okay, no question in the chat. If it's unclear, please ask now, because this is basically is going to be the whole lecture for this topic. The rest, we're just going to solve some examples and quick review of some formula for work and energy that again comes from your physics. So if there is no question, then I'm going to move on and do a quick review of kinetic and potential energy. We'll do it quick because I'm sure all of you guys know. So what we said is work is equal to energy. We show energy by E, so energy, not EE. So we show energy by E in this course, and this energy is equal to basically kinetic energy plus gravity or gravitational energy plus elastic energy. So energy then can have different forms. Of course, many types of energy, like magnetic energy and energy comes from heat and so on. But in this course, we care about this type of energy. Kinetic energy, when a mass is moving with a certain speed, and gravitational energy, the one that comes from gravity, and elastic energy, the one that comes from a spring, or let's say if we have something that has this rubbery, springy, basically elastic energy that can create a potential energy. And we call them potential energy, right? So this one then is potential, or these two, right? To be exact. So these two guys are, why it doesn't work? Okay. This is something we call it potential energy. All right. And if I want to show it in a form of formula, E, kinetic energy, we show it by T, gravitational energy, we show it by U in this course, and elastic energy, we show it by V. Some basic formula, T, you guys know the formula for T. It is half of mv squared, right? And always is positive. V can be positive or negative. So I'm going to write plus minus mgh. And you know why it can be positive or negative. Because always we can have a reference. So I'm just going to draw it here. So again, I'm sure it is not something new for you, but just have everything here on your note, clear and compact. So let's say I have a mass here, and let's say this mass moving up somewhere, and it doesn't matter if it goes straight. Oops. So it doesn't matter if this mass goes straight up to that point. So let's say it gets to that point. Or if this mass decides to go maybe on a curved path to the same height. So this is our reference. And this distance is h. the energy is going to be, U is going to be mgh. And this is going to be positive because at reference, we assume the energy is 0. Now, if this mass decides to come down somewhere here, again, it doesn't matter if it comes straight to that point or on a curvature form, it comes here. All we care is basically the distance from the reference. Let's call this one h. So this time, U is going to be minus mgh. All right. That's about U. And what about V? So V is elastic energy, right? And elastic energy is from spring. So let me then write it here. Sometimes people show it by VE, but here in this course, we just write it by V. So we know. So elastic energy or spring energy. Again, in this course, we can have, or we deal with two types of springs. One is a linear spring. Let's say a linear spring, something like that, stiffness K, and I apply a load, F. Or it can be a torsional spring, which we show it by KT. And for a torsional spring, you apply a torque, basically, like a moment, like most likely you studied it so far in your MEC 260. So we have a linear spring then. This is a linear spring. We call it a linear spring. And this is a torsional spring. Maybe you've seen torsional spring in some toys or applications. So you apply like a torsion, you try to twist it, and then there is a resistance. So for each of these, the energy, the formula for energy, this one V is equal to half of K delta X squared, or just simply we write it, V is equal to Kx squared. And everybody knows that when we talk about X, it means just the displacement, amount of displacement, all right? Or the deflection of the spring. And for this case, for a torsional spring, it is half of K. We just use this T here to remind ourselves that it is a torsional spring, right? KT. And instead of displacement now here is a theta square. And don't forget, as I said before in this course, theta has to be always in radian, okay? So you have a spring, you rotate it 90, you twist it 90 degrees, then theta or delta theta here is pi over 2. This is all we need. So this is then the total energy in a system. And basically mgh is the potential energy, half of m v squared, kinetic energy. And then if we have a linear spring, half of kx squared. If we have a torsional spring, half of kt theta squared. So we have all of these, as we discussed in previous slide. We have the conservation of work and energy law, or the law of conservation and work, which basically says you have some energy in your system. Let's call this one E1. Then you do some work on the system. So work, and as a result of this work, maybe you move the object from position 1 to position 2. So the amount of energy in your system is going to be E2, all right? Or some people like to write it as work from 1 to 2 is equal to E2 minus E1, the change in energy. They're all the same, right? Change in energy. But I like the first one because we can get a good mental picture of the process. We say our system has some energy, E1, then we do some work on it, so plus the work that we do, W, and we move it to position 2, or to a speed 2, or to whatever change in the system, we get to 2, so its energy is going to be E2, basically. All right. Any question, guys, so far? Are we good? If you have a question, please ask, because I feel this is all, again, a review for most of you guys from Physics 170. But when we get to solving problems, then we need to know how to use this one. All right, so since we are on the topic of energy, let's just quickly talk about power. So what's the difference between power and work? Okay, I'm gonna like ask you this question by showing this. Let's say I have a box, and this box on the ground right? And I apply a load, or let's say for simplicity, just a straight load, F, and the mass is M. And then because of this load, this box is gonna move, and let's say this box move to this position. And let's say this distance here is dx. Or just let's simply call it d, a distance d, all right? So the same basically system. Now let's say I have the same system, again, the same force, the same magnitude, the same distance. But this guy, the first guy, it takes maybe 10 seconds to move the box to the new position. This one, it takes 100 seconds. Is there a difference between these two? Let's take a look. The amount of work is the same, right? Work in both scenarios is the same. F multiplied by D, same. But somehow we need to take into account this time. We need to somehow show that there is a difference between 1 and 2. Otherwise, it's not fair. Let's say two people are working in a company and they are moving boxes from first floor to, let's say, second floor on a stairs. There is no elevator. So the amount of work they do is the same because the boxes are the same. And so the weight is the same and the distance is the same, the amount that they move it to the second floor. So at the end of the day, one of these guys is moving 100 bucks, the other one 1,000 bucks. There should be a difference between these two, right? And we show the difference when we talk about time. And we use a new terminology, which is power. So there is a difference then between power and work. And power defines basically how fast you do the work, or you just simply divide your work by time. Like in scenario number 1, if we divide the work by 10, we get a power. If we divide the force by 100, we get the amount of power 10 times less, which is obvious, right? The second scenario has less power. And it is important when you go buy a car, so always you need to ask, what is the horsepower on this car? And I just said horsepower, where this horsepower comes from. Initially, when people invented basically these ideas, was when like James Watt invented the steam engine. But before a steam engine, it was horses that moves carts. And people need to figure out a way to say how powerful is a steam engine. And so they compare it with a horse. So as I showed on this picture, they took a very healthy, strong horse. They call it a standard horse, maybe at that time. So maybe it's not a good term, but a healthy, good horse. And then they tested this horse on this setup to see how big it can lift basically a weight in duration of 1 second for 1 feet. So first, for example, they try a weight of 10, and this is, oh, it is super easy for this horse. It can move it in less than maybe half a second. Then they try 100 pound, and then they saw, no, it can go very fast until they got to the weight of 550 pound. So this is weight, okay, not mass. And they saw, okay, this can be it. And they call it a horsepower. So basically a horsepower is the amount of power that can lift 550 pounds 1 feet in 1 second, okay? So a crazy way that they define horsepower, but this is how they define it. Let's put it in the formula and see how we can use this basically definition in our formula. So power is then work. Work is force multiplied by d divided by time. And we know that d divided by time has a definition, which we call it velocity. So then I can write down force is equal to F multiplied by V. And don't confuse this V with energy, elastic energy. So maybe all of us, let's move back and put an E here because we don't want to get confused when we read our note. Okay, so VE to remind ourselves that we are talking about E elastic energy. All right, and maybe we put a T here, or maybe like T here to remind ourselves that we are talking about kinetic energy, VT. Oh, sorry, this is E still. My mistake. VE. Oh, it's not, yeah, V elastic energy. Okay. So let's move here. And now we know that this V that we're talking here is velocity. So in terms of unit, let's say unit. So work has the unit of Newton multiplied by displacement, right? Newton meter, which people call this one Newton meter a joule. Joule or joule, but because the inventor was a French, so joule is the correct pronunciation, but joule is okay. So basically 1 joule or 1 joule is 1 Newton multiplied by 1 meter. All right, so this is work. Then for power, has the unit of Newton meter divided by second, S, right? Because power is work divided by time, Newton meter divided by second. And in other units, again, it can be pound multiplied by feet divided by second. Okay, this is the unit for power. And people did one step further, and they call this Newton meter per second, which is equal to joule divided by second, and they call it watt, in like respect of James Watt, who invented a steam engine. So if somebody asks you what is watt, what is 1 watt, you say 1 watt is 1 Newton multiplied by 1 meter divided by 1 second. So they are all related. You should have a good care of these units and know where they comes from. Pound foot per second doesn't have a name. So sorry, it is just, we call it pound foot per second if you use that unit. And there is a relation between this guy. 1 horsepower, which we write it by HP, is equal to 746 watt, or 1 horsepower is equal to 550 pound foot per second. And to be exact, let me write it down like that. So they are all the same. 1 horsepower is 746 Newton meter per second, which this guy has a name. So it's equal to 746 watt, right? Remember, this guy has a name, and this name is watt, but this guy doesn't have a name. Maybe if I were at that time, they put my name there. Or maybe not, because I have a very long family name, right? Then imagine how miserable it was. You need, instead of just saying what here, you need to say my family name. Who, by the way, can say my family name? Do you guys even remember? No? All right, that's okay. You can just go with my first name. Everybody knows me with my first name. It's easier to remember. Okay, so any question, guys, so far here? We'll see, we're just doing a review so far, nothing special. But it's important that you have a good grasp of these. Nothing in chat. So I assume then this topic maybe is you're getting bored. And one last thing here before we move on. Guys, keep in mind, like here we had like a simple case. If I move the same things down here. So again, a quick review from your physics. If instead of like basically, let me get rid of that guy also. Okay. If I have a force which apply in an angle, let's say this is the force, and now this force basically has an angle alpha, and this is the force. You know, always you need to find the force in the direction of displacement. So then let's move this guy a little up. Okay. Then in this scenario, we know work is equal to F cosine alpha multiplied by D, right? You need to find the basically the component of this force, which you know how to do it, is going to be F cosine alpha and F sine alpha, right? So this is F sine, and this guy is F cosine alpha. And this is only F cosine alpha which is doing the work. F sine alpha is perpendicular to the movement, and it doesn't do anything. All right, with that review, so question, will this be included in the midterm? Yes, because again, this is part of a review. It's very simple. I'm gonna solve maybe a couple of quick examples today, some examples on Wednesday, and then it's gonna be like based on the question that I posted, the problem set 2, which is on this topic, and some example that I solved this week. So speaking of your midterm, which is this Friday, you need to study whatever material we cover until this Wednesday, our lecture. And tomorrow from noon to 1 and Thursday from noon to 1, I set up extra office hours, which I'll solve some extra problems. But first, if you guys have a question, you want to review a topic, I'll come back and review it for you guys. Okay, so then don't forget tomorrow, Tuesday, and Thursday from 12 to 1, I'm just going to solve some extra problems. We have our Wednesday lecture, which like on this topic, the lecture is done. It's just I'm gonna solve some extra examples. Okay, and it is included in your midterm. So tomorrow lecture will also be recorded. What about today lecture? Are we recording? I hope so. Yeah, it is recording. Please remind me, guys, if I forget to record, so I can record. Yes, tomorrow and Thursday, everything that we do in this course will be recorded and posted on Canvas, unless there is like this individual office hours that somebody comes and asks just few questions and goes. That one is not going to be recorded, but if there is like an office hour, more like several people in it, it's going to be recorded. Okay. So let's quickly solve one example together, and then we're good to go. I'll let you guys to read it. Seems very simple, right? This example, we have a box, then we have a pulley, we apply the load, we have friction, and keep in mind when we have friction in dynamics, we show it by mu k. Like we show it by mu k to say that this is dynamic, basically friction or kinetic friction. Dynamic friction. Like a friction that we counted also the motion of a particle or an object. So first things first, we need to draw a nice, clean, free body diagram, okay? And I hope you guys know from your MEC 260 to know how to draw nice and clean free body diagrams. If you want to do a quick review, I guess you guys in manufacturing and also in other programs, there is a course which Casey set it up. It is on Canvas. We call it a course, but it's not basically a course that you need to register. You just need to ask Casey or ask me to sign you up for that course. I've seen many of you in that course. It's called Engineering Skills, I believe, Engineering Skills course, which is like a free, but there is a bunch of videos for everything that you can see for SolidWorks, for like these free body diagrams. I posted some of my videos for 260 for like draw free body diagrams. So if you wish, you just need to sign up for that course. Just ask Casey I guess you guys in manufacturing know Casey. Other people, if you don't know him, just send me an email. And then you have access to the material in that course, if you like. So let's do a quick free body diagram together. Free body diagram, it means we draw everything's again, but by separating it from its base or ground. So this is the box basically. And this box is on this ground, which has so I need to drink a little bit of tea or coffee. All right. Sorry, guys. So this is the box. And then we need to carefully draw everything that we can see here. So what do I have here? So first of all, I know that I have a force P, and because they are like connected by this string, if this force is P, then this another force has to be also basically P, right? So if this is P, this is also P, and this angle is 30 degrees. So I hope everybody agree with this. And then what else do we have? Obviously, we have gravity, right? So this is our friend mg. And definitely we have the normal reaction N. And since I have friction, then we shouldn't forget like mu N. I just write mu, but we know that we are talking about mu K, mu N, okay? This is our basically free body diagram. And then it's up to us how we wanna like work on this system, like how we wanna break these forces to their components. And maybe you can break them to X and Y, but I prefer to break them to its component in basically these two directions. All right. So if I do that, then what do I get? So this mg, I know if I break it to its component, it's going to be, let me draw them by that guy. You see, I'm just breaking like these forces to their component. We'll do the same for like the other guy here, P. So what do I get then for that? So it's going to be P cosine 30. And this one is going to be P sine 30, right? So this is P cosine 30. This is P sine 30. What about this one? So let's be careful about the angles. Myself, I'll do a lot of mistake. So my suggestion would be always carefully draw the lines and make sure that you see the nice triangle before you like write the angles. So if this angle is 30, then everybody agrees that based on this triangle, this has to be 60 and this has to be 30. Okay, in that way we don't make like silly mistake. So then this guy is mg cosine 30 and this one is mg sine 30. Okay, or you can just write mg cosine 60 and mg sine 30. They are all the same. All right, so we have everything that we want. And now, since we are talking about forces, then our best solution would be to use the Newton law, like the first method, F is equal to M. But since here we have several forces, we say sum of the forces. All right, we say sum of the forces has to be equal to mass multiplied by A, because we don't have just one force here. And we can do one more thing to simplify our life. We can say that the same formula is correct if I break it down to x and y direction. So this is our x and this is our y direction. So I can write down sum of the forces is equal to m, acceleration in x, and sum of the forces is equal in y direction m a y. But we don't have any motion in y direction, right? So it has to be 0 then. But this guy, the question gave me some numbers. It says it is 5. So this is our tools, and it seems we can solve this problem. Let's do it together. So I'm going to write, let's call this one Formula 1 and this one Formula 2. I'm going to write it down here so then you guys can follow later. We will be done in 1 minute. So from Formula 1, so be careful. I write on the left sum of the forces in x. Whatever I see on the x direction. What do I see in x direction? I can see 1p. Then I can see another p cosine 30. What else do I see? Oh, I have minus mg sine 30. It is minus because it's in opposite direction. It wants to drag down this box, right? And don't forget, we have the friction. Minus mu, we replace mu by 0.25 n. And everything has to be equal to m, which is 10, multiplied by a, which is 5. Okay, good. We have some formula here, but we cannot solve it, right? So don't forget this guy is mu, which already we know what it is. And m, we know it is 10, but we don't know n and p. So we use our second tool, basically. Sum of the forces in y is equal to 0. What do I have in y direction? So I have n and I have mg cosine 30. Anything else? Yes, we have this guy, p sine 30. Almost we forget that guy, right? P sine 30. And guys, remember we are talking still about a particle. It means we ignore the size of this box. If you have a feeling that, wait a minute, this P sine 30 wants to lift this box, that's true. But that's the topic that we're going to talk about it in a week, in 2 weeks, basically, when we consider the size of something. For now, because everything is a particle, we assume that this box, this square is just one dot. So we assume all these forces are at one point. We just squeeze everything to one point, which is like, we assume everything is being squeezed to this center. Okay? So we have P sine 30, and all of this guy has to be equal to 0. Because we don't have any acceleration there. Good to go. We have 2 unknown and 2 equations. From here, I'll let you guys to go because the rest is super simple. We will find P and N. And the question asks to find P. We check our unit and everything seems to be okay. M is in kilogram. Forces is in Newton, friction good, and the acceleration 5 meter per s squared. Okay, so we're done for today. I'll see you guys tomorrow at noon. I sent an announcement yesterday. I hope you saw it yesterday or the day before yesterday, I forgot. But it is on Canvas. So let me see if there is any question on chat. I think we defined the axis on the slope. So x is along the slope. Yes, that's true. X is along the slope, right? Yes, the Fy is the forces in y direction. Why there are two P's? Okay, thanks, Brandon. Brandon says because we have a pulley, right? Yeah, thank you guys. I'm glad sometimes you guys help each other. So we have two forces because pay attention here. We have like P here, right? And then we have the pulley. So as a result, this one also is P because the question didn't tell anything about friction around the pulley. We assume if this is P, another one is also P. Okay, any other question? So yeah, there is tension on both sides. And what else? Nothing else. Okay, good. Do you guys have any question or we close the today topic? No question? All right. So let me check one more time chat. I'm gonna stop sharing. So, all right, guys, see you, most of you guys, tomorrow at noon. Again, the same Zoom thing. And please, tomorrow, if you have questions, feel free to ask. If you want to solve a problem, I can solve it for you as well. See you tomorrow. Bye.